Hello and welcome to this lesson for OCR A-Level Physics on Module 6 Particles and Medical Physics in the topic of electrical fields, looking at the concept of the motion of charged particles in electrical fields. So if we've been successful and we've learned in today's lesson, we should be able to define and describe electrical fields, calculate the electrical field strength of both uniform and radial fields, and detail the trajectory of moving charged particles entering a uniform electrical field. So we're going to be looking at the following part of the OCR A-Level Physics specification, the motion of charged particles in a uniform electrical field. So a charged particle will interact with an electrical field when it is placed in that region. So consider a charged particle placed inside a uniform electrical field, as shown here. Now a uniform field will be produced between two parallel plates with a potential difference between them. Now we know this is a uniform field as the field lines are equally spaced out and there's the same field line density throughout. Now the field lines are pointed in the direction that a positive charge would move in at that point in the field. So this means that the lines will point towards the more negative of the two plates. Now the potential difference across the two plates which produces this field is 600 minus 200, which is 800 volts. Now if we place a charged particle in the field, it will experience a force due to being in that field. This is due to the definition of an electrical field. Now the magnitude of the force can be calculated using the electrical field strength equations. This force is also a resultant force, so will cause the particle to accelerate in a particular direction. So this is the mechanism which allows a particle accelerator to accelerate particles. Now the acceleration can be determined by the following equation. F equals ma, so A is equal to F over m. Now the acceleration experienced by a particle in an electrical field is therefore dependent on the charge, as F equals eq, and the mass of the particle. So the acceleration and the charge of the particle are directly proportional to each other. The acceleration and the mass of the particle are inversely proportional to each other. And the acceleration and the charge to mass ratio of the particle are directly proportional to each other. So if we consider a particle which is already moving in an electrical field, you can see in this image the charged particle has motion. Now the particle wishes to continue in its motion, it has inertia. However, if the electrical field is acting parallel to the charged particle, a resultant force will act on the object in the same direction as motion. So this will cause acceleration by changing speed. So when the electrical field is acting in the same direction as particle motion, it will cause the particle to accelerate by changing speed. Now remember, the field lines are the direction a positive charge would take. If a positive charge is moving along a field line parallel to the field line, it will speed up in the direction of the field line. Whilst if it's a negative charge moving along a field line parallel to the field, it will speed up in the opposite direction to the field line. Now if in this situation we consider this particle which is already moving in the electrical field, once again the particle wishes to continue in its motion, it has inertia. However, if the electrical field is acting perpendicular to the charged particle, a resultant force will act on the object which is 90 degrees to its motion. So this will now cause acceleration by changing direction. So, when the electrical field is acting perpendicular to particle motion, it will cause the particle to accelerate by changing direction. This is because it is acting as a centripetal force. Now once again, remember the field lines are the direction a positive charge would take. So if a positive charge is moving perpendicular to the field line, it will deflect in the direction of the field line. If a negative charge is moving perpendicular to the field line, it will deflect in the opposite direction to the field line. Remember, in all cases, the charged particle will not change speed but only change direction, as the force is acting perpendicular to the motion. So, just clarify, if we place a charged particle in the field, it will experience a force due to being in the field. This force is a resultant force on the object. So a positively charged particle will accelerate in the same direction of the field lines, since the field lines show the direction of positive charge movement, whilst a negatively charged particle will accelerate in the opposite direction, as the field lines show the direction of a positive charge movement. Now, if we place an uncharged particle in an electrical field, there will be no acceleration, as there feels no resultant force when in an electrical field from that electrical field. Now once again, remember that the charged particle will only experience a force in the direction of the field lines. So this means it will experience no resultant force in the plane that is at 90 degrees. So in this example, the charged particle will only experience a resultant force in the vertical plane. So this means that the charged particles plot out a parabolic path in a uniform field, as only one plane of motion experiences a resultant force. Now the parabolic path occurs as there's inertia in the horizontal direction and a resultant force in the vertical direction. This is the same principle as to why objects move in a circle with a centripetal force. So we know that this means charged particles will plot out a parabolic path, which means the particles will continue at the same speed in the plane at 90 degrees to the field. So if the motion of the charged particle is perpendicular to the electrical field, the electrical force accelerates the particle by deflection. So for a charged particle moving in an electrical field, the horizontal motion is that there is no acceleration, hence the horizontal velocity of the particle remains constant with the velocity v. And the time spent in the field is therefore given by the equation distance over velocity. Whilst in the vertical motion, the vertical acceleration is caused by an electrical force. A equals F over m, so it equals EQ over m. Our initial velocity is equal to u. Our final velocity is therefore v equals u plus at, which is 0 plus EQ over m times by L over v, which we can then simplify to equal EQL over mv. As we mentioned before, if the motion of the charged particle is parallel to the electrical field, the electrical force will accelerate the particle by changing speed. This will cause the particle to maintain the same direction of motion but change speed. So what we know is that a charged particle will be accelerated in the vertical plane but maintain a constant speed in the horizontal plane. Please do note this is only the case if the charged particle is already moving. If the particle was not moving when it entered the field, it would not carry out a parabolic path. Rather, it would accelerate directly up or directly down dependent on its charge. Inertia in one plane causes a parabolic path to be taken by the particle. Now we can work out the size of the deflection if the electrical field is perpendicular to motion in the path by comparing the charge to mass ratios of different charged particles entering the electrical field. The higher the charge to mass ratio of the particle, the greater the deflection of the charged particle in the electrical field. So if we consider a charged particle in a uniform electrical field, if the charged particle is stationary when it is in the uniform electrical field, it will accelerate in one direction given a straight line path. If the charged particle is moving perpendicularly to the uniform electrical field, it will accelerate in one direction and have an inertia in the other, giving it a parabolic path. We know that because the electrical field strength is constant and is equal to V over D. We know the electrical force on the charged particle is also constant and is equal to EQ, both because they're in a uniform electrical field. We also know our work done on the charged particle is VQ. Now horizontally, there is no acceleration, the horizontal velocity is constant, and our time in the field is L over V. Whilst vertically, the vertical acceleration is A is equal to F over m or EQ over m, with the initial vertical velocity being equal to 0, and our final vertical velocity is V equals u plus at, which simplifies to EQL over mv. So, if we consider a charged particle moving perpendicularly to a uniform electrical field, horizontally, our acceleration is 0. Vertically, our acceleration is EQ over m. Horizontally, our initial velocity equals our final velocity, whilst vertically, our initial velocity is 0. Whilst our final velocity vertically is EQL over mv. Whilst our time in the field can be worked out via looking at the horizontal motion, which is equal to the length over the velocity of the object. Remember, horizontally, there's no resultant force, whilst vertically, the resultant force is the electrical force. Now this means vertically we have a constant acceleration in this plane, whilst horizontally we have inertia in that plane. So to summarise what we've looked at in today's lesson, we've looked at the motion of charged particles in a uniform electrical field. So if we've been successful and we've learnt in today's lesson, we should be able to define and describe electrical field strength, calculate the electrical field strength for both uniform and radial fields, and detail the trajectory of moving charged particles entering a uniform electrical field. Thank you so much for watching this lesson, which is part of OCR A-Level Physics, Module 6, Particles in Medical Physics, in our topic of electrical fields, and on the concept of the motion of charged particles in electrical fields. Thank you so much for watching, and have a lovely day.